Hello. Now we are in a stage to begin the geometric group theory part of this course. We'll first review what we have done so far in this course. Then I will elaborate the topics that will be covered in this geometric group theory part. Let us begin. We have started with first the axioms of Euclidean geometry. And this hyperbolic geometry, it grew out of attempts by geometers to prove the Euclid's fifth postulate, so that is the parallel postulate. Some geometers tried to prove it by assuming the negation of the parallel postulate and tried to arrive at a contradiction. So in 19th century, around 1830, Lobachevsky, Bolyai, and Gauss, so they discovered a new geometry, so which was initially called to be non-Euclidean geometry. And this name, it was given by first Gauss. And at that time, so there were no models of this non-Euclidean geometry. So in 1868, Beltrami, so he gave some models of hyperbolic geometry. And the term hyperbolic geometry, it was introduced by Klein in 1871. So to get a history of this hyperbolic geometry, you can refer to this article by John Milner. Okay. So now let us again see this upper half plane model of this hyperbolic space. So we have started with this upper half plane, and we have put this hyperbolic metric, which is dA squared is equal to dx squared plus dy squared by y squared. So given this metric, you can compute the length of any path alpha. So suppose alpha t is xt comma yt. So then alpha, length of alpha, it is integration 0 to 1, where the unit interval 0, 1 is the domain of alpha. It is the integration, length of alpha, it is the integration 0 to 1 root over x prime t whole square plus y prime t whole square divided by yt square dt. And this length of alpha, so this we have proved, it is greater than equals to mod of log p by a. So alpha 0 is equal to the ordered pair 0a, and alpha 1, it is equal to the ordered pair 0b. And now if I take this vertical path gamma defined from this interval 0 to log p by a to h2, so defined by gamma s equal to this ordered pair 0 comma a e to the power s. So this s, in fact, it is the length parameter here. So you can compute the length of this gamma. It turns out to be equal to mod of log b by a. So this gamma, it will be a geodesic, because length of alpha is greater than equals to length of gamma, and and length of alpha, it is always greater than equals to mod of log of b by a, and gamma is the path whose length is equal to mod of log b by a. So therefore this gamma, it will be a geodesic. So the vertical paths are geodesic. And now if I take any Mobius transformation like this, fz is equal to az plus b by cz plus d, where this a, b, c, d are real numbers. And if I take this ad minus bc equal to plus minus 1, so this Mobius transformation, it acts by isometry on this upper half plane. And the property of Mobius transformation tells you that if you take any circle or a straight line, so this Mobius transformation, it will take that circle or straight line to another circle or straight line. So therefore, so this geodesics are vertical axis and semicircular arcs with center on real axis. And from here you can see clearly that the fifth postulate of this Euclidean geometry is violated. So given this point P and a geodesic L in this hyperbolic plane such that P is not in L, so there exist infinitely many geodesics passing through this point P not intersecting L. So there is another model called disk model. So this we have discussed. So this is also called Poincare disk. So consider this unit disk and you again put this metric d squared, which is equal to 4 dx squared plus dy squared divided by 1 minus x squared plus y squared whole square. So given this metric and suppose you have this map from h2 to d2. So if z is equal to z minus I by z plus I. So now this h2 is equipped with a metric and d2 is equipped with a metric. So this map F, it is an isometry. And this geodesics in this disk model are diameters and circular arcs which intersect the unit circle orthogonally. Also note that this unit circle is at infinity in this unit disk, and in the upper half plane model, this line R union infinity, this is also at infinity. This is not at a finite distance from any point of the upper half plane. Let us see the difference between this hyperbolic plane and Euclidean plane. In hyperbolic plane, triangles are uniformly slim. So that is, there exists a non-negative number delta such that any side of a triangle is contained in delta neighborhood of union of other two sides. If you take the upper half plane or the Poincare disk, so this delta is equal to log 3. In Euclidean plane, triangles are not slim. So the triangles are here very fat. By fat, I means these triangles are getting bigger and bigger in this Euclidean plane. In hyperbolic plane, also we have seen that some of the vertex angles of a triangle is less than pi. Whereas in Euclidean plane, sum of vertex angles of a triangle is equal to pi. And this fact we have not seen, but it can be checked if you have done Riemannian geometry. Curvature at each point of this hyperbolic plane is -1, whereas the curvature at each point of this Euclidean plane is 0. So, okay, so after learning this hyperbolic plane, so we have learned about isometries of this hyperbolic plane. So if you take the upper half plane model, so the group of orientation preserving isometry is isomorphic to PSL to R. And so then we have discussed about Fauchian groups, so which are discrete subgroups of this PSL to R. So this name Fauchian is first given by Poincare. So he was motivated by the work of Fuchs in 1880, and after that he gave the name of this Fauchian group. Okay, so now let us recall. So what is the definition of this properly discontinuous action? So an action of a group is said to be properly discontinuous if for any compact set K, so the set G belongs to this group, K intersection G is non-empty, so this set is a finite set. And we say that the action is co-compact. So if there exists a compact set K such that union of GK is equal to X. So GK means that it is the group G is acting on this space X, and if you take an element small g in this group capital G, so G dot K means it is the action of that element on this compact set K. And a subgroup G of PSL2R is said to be Fauchian group if the action of G on this upper half plane is properly discontinuous. So equivalently, if you take any orbit, so that will be a discrete subset of this upper half plane. So these things already we have seen. And what are examples of this Fauchian group? So if you take PSL to Z, so that is a Fauchian group. That is, in fact, it is a discrete subgroup of this PSL to R. And we have talked about elementary Fauchian groups and non-elementary Fauchian groups. We have proved that surface groups are non-elementary Fauchian groups. So let us again see into that thing. So what we have proved that if I take any surface which is compact and without boundary, and suppose the genus of that surface is greater than equals to 2, so then it admits a hyperbolic metric. So for instance, if I take S2 to be a closed surface of genus 2, so this is obtained as a quotient space of regular geodesic octagon. So like this, it is given in this picture. So here you identify the side B1, B4 with the side B2, B3 by an isometry. So there exists an isometry A which takes the side B1, B4 to B2, B3. And you proceed similarly for the other edges. So you will have a side pairing of this geodesic octagon. So as a quotient space, you will get the genus 2 surface. And also we have seen that the fundamental group of this genus 2 surface is nothing but the group generated by A, B, C, D, and it is a one related group, and the relation is the product of the commutators is equal to 1. So A inverse, B inverse, C inverse, D inverse is equal to 1. So that is the relation. So this fundamental group, so this in fact we have proved that it is a subgroup of PSU11 or PSL2R. And this in fact, it is a Fauchian group. So that thing we have seen. So fundamental group of S2, it acts freely, properly, discontinuously. And in fact, the action is also co-compact. So pi1 of S2, it acts by isometries on the Poincare disk, and the action is free, properly discontinuous, and co-compact. So therefore, we get an 8-8 tessellation of this unit disk, and we have proved that this surface S2 admits a hyperbolic matrix. So using the covering space theory. So similarly, if I take the puncture surface, sigma 1, 1, it is the surface with one puncture and one genus. So that is your puncture torus. So pi 1 of sigma 1, 1, it is free group with two generators AB. And we have also seen that it acts freely and properly discontinuously by isometries on this Poincare disk, and hence it is Fauchian. And so you can check that the commutator here, so A, B, A inverse, B inverse. So take the cyclic subgroup generated by this commutator A, B, A inverse, B inverse. So this, in fact, it will preserve the Horo disk C in this picture, so that you can check. So yeah, let me move to the other slide. Okay, so now let us move to geometric group theory part. So this geometric group theory, it is the branch of mathematics that studies finitely generated group. with its action on geometric objects like Euclidean space, hyperbolic space, trees. For example, if I take Z2, so it has a natural action on R2, the R2 with the Euclidean metric. So Z2 is acting on R2 by translation, so that is a natural action. And for example, if I take fundamental group of genus 2 surface or any higher genus surface, it acts nicely on this hyperbolic plane. And if I take free group with 2 generators, or if you take just the cyclic group, infinite cyclic group, it acts on the real line R. And if I take the free group with 2 generators, it will act on a regular tree such that the degree of each vertex is 4. So yeah, so we'll see this thing in this course. So this subject geometric group theory, it was popularized by the work of Gromov in 1987. So he discovered this hyperbolic groups. So this so what do you mean by hyperbolic groups? So these are groups whose Kelly graphs are hyperbolic metric spaces. So we'll be dealing with these hyperbolic groups in this course. And this hyperbolic metric spaces, so these are generalization of this hyperbolic plane. So these are central geometric objects in geometric group theory, so which captures the negative curvature of a metric space. Okay, so let us just quickly see the definition of all this stuffs. Okay, so the slim triangle already we have defined in hyperbolic plane. So in a metric space, you can also define the slim triangles. Yeah, so you start with a non-negative number delta. So a geodesic triangle is said to be delta slim if each side is contained in delta neighborhood of union of other 2 sides. So this delta slim property of for the triangles that you have seen in the for the upper half plane with hyperbolic metric. Now, so what do you mean by a delta hyperbolic metric space? So a geodesic metric space is said to be delta hyperbolic if all triangles are delta slim. Okay, so already we have seen that this hyperbolic plane is log 3 hyperbolic metric space. So all the triangles in hyperbolic plane are log 3 slim. So now if I take any tree, so what is a tree? So it is a graph without any cycle. So a tree is a 0 hyperbolic metric space. So it means that if I take any triangle here, so that it will be a tree generated triangle. So delta will be 0 here. So a tree is a 0 hyperbolic metric space. And so what is a non-example? So if I take take Euclidean plane, so obviously it is not a hyperbolic metric space. So the triangles are not slim there. And in fact, you can build many space from this this Euclidean plane which are not hyperbolic. For example, if you take this E to be Euclidean plane and L to be an infinite line, and you take the West sum of this E and L. So this this plane E and L intersecting only at a single point here, C. So because this Euclidean plane is isometrically embedded in the space, so this will be not a hyperbolic metric space. Although, so this space has a part which is L, which is a hyperbolic metric space. So L is just a tree. So L is a hyperbolic metric space, but the whole space is not hyperbolic. Okay. So we'll be also dealing with this type of maps which are called quasi-isometric. So a map phi from x to y is said to be k epsilon quasi-isometric. So if this inequality first it is satisfied, so that is 1 by k times distance between x comma y minus epsilon is less than equals to distance between phi x and phi y is less than equals to k times the distance between xy plus epsilon. So if this inequality is satisfied, we call this phi to be quasi-isometric embedding. And if this condition B is also satisfied, so then we call it to be phi to be quasi-isometric. So phi is said to be k epsilon quasi-isometric if for each y, so there exists x such that distance between y phi x is less than equals to k. So okay, so a map phi is said to be quasi-isometric. So if phi is quasi-isometric embedding, and the second condition is also satisfied. So yeah, so for each element y in the codomain space, so there exists an element x in the domain space such that the distance between y and phi x is less than equals to k. So one can prove that if I take lattices in R2 of rank 2, so they are quasi-isometric to R2. So here R2, I am taking the Euclidean metric. So in this course, we'll be dealing with quasi-geodesics also. So what are quasi-geodesics? So you take any interval, closed interval AB, and alpha is a map from this closed interval to a metric space X. So alpha is said to be k epsilon quasi-geodesic. So if this map alpha is just a k epsilon quasi-isometric embedding. Okay, so note that, so this quasi-geodesic, it may not be continuous map. So we'll be proving the stability property of this quasi-geodesics. So what is that thing? So a quasi-geodesic and a geodesic joining same pair of points in a hyperbolic metric space lie in a uniformly bounded neighborhood of each other. So this fact is called stability of quasi-geodesics. So using this thing, we can prove that hyperbolicity is quasi-isometric invariance. So that is, so if you are given a quasi-isometry from x to y, and suppose you know that x is a hyperbolic metric space, so then y will be also a hyperbolic metric space. Okay. So we'll learn about Kelly graph. So these are the graphs corresponding to groups. Suppose we take this finite generated group G. So let S be a finite symmetric generating set of a group G. So the graph gamma G, whose vertex set is G, and S set consists of pairs G comma G prime, such that G inverse G prime belongs to S is called the Kelly graph of G. So this will be doing in details. And now corresponding to a finitely generated group, we can have two generators. So suppose S and S prime are two generating sets of the same group. So then what we can prove that the Kelly graphs, this gamma and gamma prime, so they are quasi-isometric to each other. So there is a well-celebrated result due to Milner and Swark. So take a finitely generated group G, and suppose it acts properly and co-compactly on a proper geodesic metric space X. So then one can prove that the Kelly graph of this group G is quasi-isometric to X. So here are some examples of Kelly graphs. So if I take the free group with two generators A and B, so this infinite tree such that the degree of each vertex is equal to 4 is the Kelly graph of this free group with two generators. And if I take Z2, so then this lattice of rank 2, square lattice of this rank 2, it is the Cayley graph of this Z2. Okay, so now what is the definition of hyperbolic group? So a finitely generated group is said to be hyperbolic group. So if a Cayley graph of G is a hyperbolic metric space. So start with a group G and also assume that this group G is finitely generated. And if its Cayley graph is hyperbolic metric space, so then we call this group to be hyperbolic group. So for examples, if I take free groups, so as I said before that Cayley graphs of free groups are trees, and trees are hyperbolic metric spaces. So therefore, these free groups are hyperbolic. And this fact already we have seen. So this fundamental groups of closed orientable surface of genus G greater than equals to 2. So this acts on this Poincare disk properly discontinuously and co-compactly. So using Milner's work lemma, this fundamental group of this surfaces is quasi-isometric to this Poincare disk. So therefore, the fundamental group of this closed orientable surfaces of genus greater than equals to 2 are hyperbolic. And what are non-examples? So if I take any group which contains z direct sum z or z cross z, so that group will be not hyperbolic. So we'll learn about properties of this hyperbolic groups. So one of this thing is, so if I take an infinite hyperbolic group, so you can prove that there exists an element of infinite order. So we'll learn about quasi-convex subgroups of this hyperbolic group. So a subset Y of a geodesic space is said to be epsilon quasi-convex. So this number epsilon, which is non-negative, it is already pre-chosen. So if so a subset Y of this X is said to be epsilon quasi-convex if any geodesic joining 2 points of Y lie in this epsilon neighborhood of Y. So any geodesic means, so this geodesic joining 2 points of Y, so this geodesic it will be in X. So that geodesic it will lie in epsilon neighborhood of Y if this Y is epsilon quasi-convex. And a subgroup H of G is said to be epsilon quasi-convex. So if it is epsilon quasi-convex in the Cayley graph of G. And we'll study some properties of this quasi-convex subgroup. So a cyclic subgroup is quasi-convex, is always quasi-convex in a hyperbolic group. And we'll prove that intersection of quasi-convex subgroups is quasi-convex. And for reference, we'll refer to this two things. So first one is the book by Peterson and Hepliger. The title of the book is Metric Spaces of Non-Positive Curvature. And we'll also follow this note by Bowditch. So the title of this note is A Course on Geometric Group Theory. Okay, I'll stop here.